This is a help video for the Laplace Analysis Game in Circuit Tutor, Level 3, Problem Type 2. So we're going head into that game now. And of course, before you begin, you should have already reviewed the introductory tutorial on Laplace domain circuit analysis, which is under the Laplace impedance simplification game, as that contains a lot of crucial information for solving this type of problem. So we'll assume that you've already done that. And now we're going to go ahead and select the appropriate problem type here. Now, we always recommend that you look at some examples prior to starting the problems yourself. That will generally give you a lot of good information about how to work the problems. So for right now, in the interest of time, I'm going to go straight into a problem. So we'll go ahead and generate a problem here. And this is going to be a problem type where we need to solve using source transformations as the solution method. So I'll wait for that to go ahead and load here. So doing a lot of computations in the background. Okay, so I'll wait for that problem to be displayed. Here we go. Okay, so here's our problem, and you see it's being presented, of course, initially in the time domain, where we have several sources that are step function sources of time. So as always, we're solving transient problems when we do Laplace domain circuit analysis. That's a very important thing to keep in mind. Now the first step here, because we are in the time domain, remember we have a reactive element here in units of farads. Farads are henries, and also the presence of time. All of that indicates that we're in the time domain. And also our sought variable is a function of time. In the Laplace domain, notice that the sought variable has already been converted from a function of time, little v naught of t, to a big capital V naught, which is bold, indicating that that's a complex valued Laplace quantity. So that is no longer a function of time, and when you're doing this by hand, that should never be written as v naught of t, because t cannot exist anywhere in the Laplace domain. Okay, so let's go ahead and convert the sources here. So this v1s of t, we see that that is a unit step function for u of t. And remembering that the Laplace transform of that would be 4 over s. We can enter that. And if you don't remember that for any reason, you can always pull up the Laplace transform table using this button here. Okay, then we'll convert the capacitance. And remember, the impedance of a capacitor is 1 over sc, where s is the complex frequency and c is the capacitance. So here that will be 1 over parentheses 5s. And notice I have to have parentheses there around the entire denominator, otherwise I'd be writing 1/5 times s, which would not be the correct answer. Okay, then we'll do a similar thing. We'll convert the current source here, I1s of t, which is 7u of t. We'll take the Laplace transform of that, and that becomes 7 over s, similar to what we did for the voltage source here. And the second voltage source, V2s of t, that's 6u of t, so that will just become the 6 over s in the Laplace domain. And then the resistors, of course, are unchanged. Okay, so we're done with that, so we'll click Done Converting to Laplace domain, and that'll check our values, and it says that they're correct, so we'll go ahead, and it'll replot that now for us in the frequency domain, and then we'll be able to proceed with solving this using source transformations. Okay, and it does advise that we do need to go in and simplify the circuit, so we'll go ahead and do that. Now there was one glitch here with this particular button, sometimes goes blank, and some of these other buttons occasionally go blank, which is a system glitch that we can't control, but we can still use the button normally. So we're going to go ahead into the circuit editor by clicking on Simplify Circuit. And so now we're in the circuit editor in the Laplace domain. Notice that we have the previous circuit here always for reference, so that'll help be a useful thing when we're doing source conversions. And usually it'll also bring up some help items telling us about how we need to right-click on elements to do various things, and also we can use these shift or compress or stretch buttons if we need to make more room, for example, to do the operations we need. Now, looking at the circuit, before we try to do any source transformations, we always want to start by combining anything in series and parallel that can be so combined, because that's really the only reason we do source transformations, is to permit that combination. So if we look carefully here, there are no voltage sources in series, and there's only one current source, so that of course can't be combined with another current source. And in terms of things in series and parallel, we can spot only two things that are in parallel here. There's nothing in series, well, no elements of the same type in series anyway. So we do have two impedances that are in parallel, namely the 1/5 ohms and the 7 ohms. Those are both connected to this bottom node here and this upper node here, and therefore they're in parallel, so we can combine them. So I'm going to go ahead and do that, and just to show the mechanics of that here, I've done that on paper. So we have two things in parallel. We'll use the product over sum formula in this case, which is valid if you have just two elements, not for 3 but for 2. And so 7 times 1/5s, this is all in ohms, divided by the sum of the 7 plus the 1/5s. And now, as usual, you want to clear any fractions that occur inside fractions. So we'll multiply both the top and the bottom of this by the common denominator, which is just simply 5s here. So in the top, we just get 7 after multiplying by 5s. In the bottom, we multiply by 5s, and 5s times 7 gives us 35s, and then this just becomes 1. And so we have 7 over the quantity 35s plus 1. So I'll go ahead and enter that. And we'll put in parentheses there. It should be sufficient. Or I could use square brackets, either one. But I do need to use something there, because otherwise we would only be dividing 7 by 35 and not putting the rest of it in the denominator where it belongs. Now notice that's still colored red, meaning there's something wrong. And it actually tells us that that's because this is no longer an appropriate type of impedance for a capacitor. This is a more general impedance, so we now have to convert that symbol from a capacitive symbol into a generic impedance, which is this rectangular box. And so once we've done that, that fixes that problem. And then the 7 ohm now is being combined into that, so we have to change this, remember, to a short circuit. Now we never would change that to we need to change it to an open circuit. I was going to say we never change it to a short circuit, because that would short circuit the new impedance, and that was not how it was to begin with, of course, so that would be absolutely wrong. So we need to use the delete key there to do that, or you could right-click on it and click the delete option. And now we'll check that combination, and that was correct. Okay, so now we see that we've combined everything in series and parallel that we can really do, and so that's an indication that we need to start looking for source transformations. Now, there's several that are possible here. You might notice we always need a voltage source in series with an impedance, or a current source in parallel with an impedance. Those are the only things that can ever be transformed. Here we do have a voltage source in series with a resistor. However, that resistor has our sought variable, and you have to remember that you never want to try to do a source transformation on an element that contains a sought variable, because that variable would no longer be there after the transformation, and so that must be left alone. Now we could also transform this current source in parallel with an impedance, but as you can probably see, that wouldn't really do us any good, because we then have a voltage source, for example, here in series with the impedance here connecting the top and the bottom nodes, and that does not allow us to do any new combinations that we can't already do. So that would, while it's possible to do, it wouldn't be useful to do. In fact, it would be counterproductive. So that leaves us with this choice, which is a voltage source in series with an impedance. By transforming that, we'll put things in parallel, as we can see, and therefore that would be useful. So I'm going to take this voltage source, I'm going to move it up over here, just to kind of align things and make it a little easier. I'm going to move that wire up there where I'm going to need it, and then I want my 3 ohm to be in parallel with this, what's going to now be a current source, and I'm going to move that wire up here just to finish connecting that, and then I'll have to add a new wire down there, so I'll click on Add New, which by default is a short. And now we need to change this voltage source. Since we're transforming it, we need to change it into a current source. So I'll click on the current source icon, or I could also use the drop-down element type thing and do it that way. Either way will work. Now that's pointing down, and we notice the positive sign was on the bottom here before. That is connected to this node, and indeed, which has now basically become this node. So that is correct in terms of the polarity, so we'll leave that alone, otherwise we'd reverse it here. And now to compute the value of that current source, we divide the voltage source by the impedance. And so I've just done that on paper. It's very simple, really. 6 over S divided by 3. So the 6 by 3 is 2, and then the S now is in the denominator. So that will simply be a 2 over S step function type of source. Okay, so that should complete the source transformation. So I'll click on check that, and that is correct. And now we see that we have an abundance of things in parallel on this part of the circuit. So we can start combining those, whichever we prefer. And so, for example, let's look at the current sources. So this one, these are both connected to the same pair of nodes, so they are, of course, in parallel. They therefore can be combined. This one is pumping positive charge from the bottom node to the top node, whereas this one is pumping positive charge from the top node to the bottom node. So we see that those are actually fighting each other. They're not doing the same thing, they're doing opposite things. Therefore, we will need to subtract their values rather than add them. And so we'll maintain the bigger of the two values and use that polarity. And so 7 over S minus 2 over S will, of course, just be 5 over S, since they both have the same denominator. And so then this current source now, we have to think about this carefully. This needs to become zero current because we put its current effectively over here by reducing this value. And so we want to make this zero current. Remember, zero current is an open circuit, not a short circuit. Once again, if we shorted this, we'd be destroying a large part of the circuit, which would certainly not be correct because that was not the case originally. So I'm going to, well, I can use the delete key, or I can do it with the right-click menu, either way. Okay, so we've combined those current sources. We'll check that combination here with this button, and that is correct. And now we see, well, we also have two impedances that are in parallel. We have the 7 over quantity 35S plus 1 and the 3 ohm. So I'm going to combine those in parallel, and I've written that out here. So I'm going to use the reciprocal over sum of reciprocals formula in this case, which is equivalent to the product over the sum. I just chose to do it a different way here to illustrate. So I first take the reciprocal of this one, and so that means that now the 35S plus 1 has to be on the top, and the 7 needs to be on the bottom. So it's very important to take that reciprocal. Sometimes people, not infrequently, forget to do that, and then of course you'll get the wrong answer. And then the 3, again, we must take the reciprocal of that to put it in the 1 over the sum of reciprocals, so that becomes 1/3, not 3. Okay, having done that, we then examine the bottom. We see, well, we need a common denominator that will obviously be 7 times 3, since those are both prime numbers. There's no common factors. And therefore, that'll be 21. So I'm going to multiply the entire top of the fraction by 21, and then the bottom by 21 as well. So that effectively multiplies this by 3. It's 3 times 35 is 105. 3 times 1 is just 3. And then over here, I have to multiplying by 21, just effectively multiplies this by 7. And so we get a 7 here. And the 3 cancels out. And so then we can simplify that to 21 over just 105S plus 10, just combining the constants. And actually, when we enter that in Circuit Tutor, you notice there is a common factor in the denominator. It always likes to have you factor out common factors. The reason being that it might cancel something in the top. Now, it's not going to do that here, but sometimes it will, and you don't really know until you've done it, I guess. So here we see that this has factors of 2 and 5, and this certainly has a factor of 5, but not a factor of 2. So we see that we can pull out a factor of 5 there. So I'm going to enter that combined impedance. I'm just going to, I could put it either here or here, but it's easier to do it here since this is already generic impedance. So I'm going to enter 21 over, and now I'll have a square bracket because I'm going to factor out my 5 times the S plus 2 now. And then I'll close the square bracket. And remember, anytime we have a product of factors in the denominator, they have to be inside a square bracket. We're not allowed to use parentheses inside parentheses at this time. So, and the 21/5, that's acceptable because those are both integers, so it will allow you to do that. Okay, then the 3 ohms needs to go away now because that was combined into this, and so once again this changes to an open circuit, not a short circuit. Again, we want this to basically become an infinite impedance in parallel, so that it no longer affects this one. So I'll just press the delete key there, and then we'll check that combination here. Okay, so I may have, oh, I left out the 21s. I meant to write 21s there. So that was supposed to be a 21s because I was factoring it out, and I just neglected to type the 21. So that's the correct answer there. So we'll try that again, and that is correct. Okay, and that's one of the reasons we allow a few mistakes here, is that it's easy to make a silly typing error. Okay, so now if we look at this, there's nothing in series and nothing in parallel. Again, we can't transform this because that would lose our sought variable. So we have to leave this alone, and instead we'll make another source transformation here to make this one of our Holy Grail type circuits, which is a single loop circuit. So that means I'll change this into a voltage source now, and to do that I'm going to change that. Well, I'll just change it first, and then I want its polarity to be the plus side on the top to be consistent with the head of the arrow there. So I'll click the reverse polarity button, or you can also do that by right clicking. And then the value, I need to multiply the current source value times this impedance. So I've done that here on the paper. So we have the 5 over S amps times the 21 over, well, I wrote it here as 105 S plus 10, but really we can factor out the 5. The 5 will cancel with this 5, and then we end up with a 21 over S times the 21 S plus 2. So that'll be the product there after we combine those. So I'm going to go ahead and type that. 21 divided by, and again I need a square bracket to enclose the product of factors. So that'd be S times 21S, remembering 21 this time, plus 2, closing the square bracket. And that's the value of the voltage source. And then of course we need to put the impedance now in series. So I'm going to delete this short after clicking on it to select it. See how it's red? And I can delete that with the delete key, and then I can just click and drag that. In other words, I'm holding my mouse key down as left mouse key down as I drag that over here. Okay, so now you see I have a single loop circuit, and I need to check that source transformation, and I'll just verify that that looks like that should be correct. And it is correct. And so now I can simplify further, because now I have two voltage sources, for example, that are in series with each other. Even though they're not directly connected, it doesn't matter because they're part of the same loop. They belong to the same pair of meshes, the inner mesh and the outer mesh, so clearly they have to have the same current, since they have the same two mesh currents, and they are in series. And we can also think about, well, should they be added or subtracted? So this one, for example, has a plus sign. If we go, for example, counterclockwise, we encounter the minus sign first, and here we encounter the plus sign first. So that means these have different polarities. Or alternatively, you can think of it as this one will make current go from the positive side. Just as water flows downhill, it'll go through the passive elements in a clockwise direction back to the source, whereas this one would do exactly the opposite. It would go from the high side of this source counterclockwise back to the negative side, as it goes, always water goes downhill through a set of troughs, for example, as these passive elements would represent. It goes uphill through the source, but downhill through the trough. And so therefore these are fighting each other, so we need to subtract their two values. So I'll take the 21 over S times 21S plus 2 and subtract the 4 over S here, and then we will need to put that over a common denominator anytime you add or subtract fractions. So our common denominator will just really be the denominator of this, since that already has an S in it. So you have that common factor. So therefore I just have a 21 over the common denominator minus then the 4 I need to multiply by the 21S plus 2 factor. And then of course you can always check that by just dividing back. So you see 21 over that product is what we had here, and then minus the 4, and then these terms cancel out, and you have the 4 over S that we started with. So you can easily verify that's correct. Then of course we can simplify this. We can take the minus 4 times 21S is minus 84S. And again, I always want to write these just in standard form, which means you put the highest power of S first, not last, is the preferred form algebraically, just to keep your work well organized. And then you here have the 21, and that's going to be minus 4 times 2, or minus 8. So 21 minus 8 is 13. And then just the denominator carries over. Okay, so we can enter that as our combined source value, and I'm just going to do that here, and I want to be consistent with the value of the original source because that's how I got this value. So I need to replace this one and not this one, otherwise I'd have to put a minus sign in there as well, which we could also do. But let's just do it here. Okay, so I'm going to put parentheses, negative 84s plus 13. Again, I need parentheses in the numerator to keep all of that in the numerator and make a single rational function, ratio of polynomials. And then again, square bracket here, and then a factor of s times a 21s plus 2. Close parentheses, and then close the square bracket. Again, I always need the outer ones to be square brackets if the inner ones are parentheses, except where I have a simple numerical fraction. Okay, then this one, since that voltage now, I've transferred that voltage effectively over here, and therefore I need to make this 0 volts, which is going to be a short, not an open. An open would wreck the whole circuit, and that clearly isn't what we should be doing here. So that becomes a short, and then we'll check that combination, and that is correct. Now, I don't want to combine these two because that would lose our sought voltage, and in fact there's really no reason because this is already a simple voltage divider. So I'm just going to leave that as is, and that should be fine. So I'm just going to click Done Editing here. And that'll take us back into the main form. And so now, because this is a single loop circuit, we can choose the single loop form of analysis. Or if there was no loop at all, we could use the no loop option. It's the same thing. And then we're going to select the option to enter a sought branch voltage, because that's the only thing it'll really let us do here. It doesn't want us writing KVL equations and things when we don't need to, because we can just directly use the voltage divider formula for this. So we have V naught is equal to, and now we want the voltage divider formula, and you remember that's going to have this form, where we have the input voltage, that's the source voltage here, multiplied by the impedance of interest divided by the sum of all the impedances in the circle. So now, first of all, we need to think about polarity. Polarity is always important when using this type of formula. So we need to check how the polarity matches up. Since we use this source, we see the positive side is connected to the negative side of our sought voltage, and the negative side of the source goes to the positive side of the sought voltage. That means that this is going to be, the current's going to be going counterclockwise here, which is the active sign convention for this element. Therefore, we need to have a minus sign out front. If we fail to put in that minus sign, we will get the wrong answer. So I'll put that in provisionally. Then the source value will be this V1s. Now, in this case, and the program actually factored out the minus sign here in front for us and just pulled the minus sign out of the entire factor. So it made this negative. And that's actually a little bit better way to write it. So because it's already negative, I'm actually going to change this back to a plus in order to negate it. And then we'll just put in the value without the minus sign. That way it's an easier way to do it. So we'll go parentheses here, 84s minus 13, close parenthesis, and now put in the denominator, which again needs the square bracket for the product of terms, s times 21, oops, sorry, I got too many parentheses, 21s plus 2, close parenthesis, close bracket. So there's our source value with the minus sign incorporated. And then we want our impedance of interest. So that's going to be the 9 ohm, because that's where our sought voltage is. So we put 9 there. And then we'll put that also here. And then the other impedance would appear over here. So that's going to be, and of course the order doesn't really matter in the denominator, but I'm just going to put them both in. So that's going to be the 21 divided by, again, the bracket, the 5 now, times 21s plus 2, close parenthesis, close bracket. And so that should be the correct answer. And again, just physically think about this as being the voltage divided by the sum of the total impedances. So this term altogether is the current, which is going in the circuit. And then we multiply that times the impedance to get its voltage. And of course, the minus sign takes care of the signs appropriately. So we'll check that equation now. And that is correct. And now we're done entering all the equations we can. So this is actually the no more equation button. So that's what we're going to have to click, even though it's unfortunately blank right now. And now it's going to advise us that we want to factor any quadratic terms, which we're actually not going to have here. But we also should really rationalize any linear terms as well. It doesn't mention that, but that's also should be done in preparation for doing partial fractions. Because remember, we always want terms of 1 over s plus a as opposed to 1 over as plus b, for example, for which there is no table entry. So we'll compute that over here. We'll simplify this expression. So our v naught is, I wrote here just with a minus sign and a minus 84 s plus 13 times now the 9 in the numerator, and then we have the s and the 21s plus 2 factor, and then we have this just written out again. So I've just recopied that. And now to simplify here, what I've done is I've just basically, I've kept the minus sign outside for the moment, multiplied the numerators, and I just decided to use this factor to multiply by this, since that'll cancel out this factor over here. That makes it fairly easy to do. So I'll keep the s, which has to be there. And then first I get 9 times the 21s plus 2. So the 9 times 21 is 189, plus 9 times 2 is 18. And then we have 21, still the 5 here, remember, because that we didn't, basically didn't normalize out. So we have 21 fifths, which can be written as 4.2. Right? In other words, 42 tenths or 4.2. And then to simplify that a little bit, I just rearranged it here. And I combined the two constant values. So we have 189s plus 22.2 there. And now, basically, I want to rationalize the denominator, which means I want to make the coefficient of s there be 1 in preparation for the partial fraction expansion. The top one doesn't matter so much, but the bottom one does. So we'll divide both the top and the bottom by 189. That way, we'll make this equal to 1. So as we divide the bottom by 189, then we have s times just s, and that 22.2 divided by 189 on a calculator, you can work out that that's 0.01175. And again, always check these numbers when you're doing the arithmetic on a calculator. Look at the number and make sure it's actually reasonable for what you should have gotten, right? That's a way to make sure you didn't make a mistake with a decimal point or just typing the number or something like that. So always look to make sure the number is reasonable. And you can see, I think, by inspection that is pretty reasonable, because this is a little more than a tenth of that. So when we divide, we should have something like that. And then in the numerator, we also have to divide by that. And so basically we'll get, dividing by 189, that will work out to be just 4s. And then we'll have the second term becomes basically, if you multiply that out and divide by 189, becomes minus 0.619. And now we have the denominator rationalized, and so that's a good form to enter here for our answer. So we'll put in parentheses 4s minus 0.619. I like to use a leading zero to make sure we can notice that there is a decimal point there. And then the solidus, and then we have the left bracket, and we have s times s plus 0.1175, close parenthesis and close bracket. And just checking, that should be correct. So we'll enter that. And that is correct. And now it tells us the next step is to do our partial fraction expansion in order to do the inverse transform to get back to the time domain, which is, of course, our goal. We're trying to solve this transient problem in the time domain is our ultimate goal here. So we'll select the only option, which is to do a partial fraction expansion, and it'll provide us with the terms that are needed for that. So we'll have v naught of s equals. And then because we have two terms in the denominator here, we know the partial fraction expansion is going to look like this. We're going to have a constant a over s and a constant b over this other factor. So we've written that out here. So I'll just enter two terms here for now. And they're both going to have units of volts, since this is a sought voltage we're looking for. So we'll change the amp slash volt slash watt indicator to a volt. That's a volt. And then we'll come over here to do the partial fraction expansion on paper. So we'll use the heave-aside method, or the method of residues. So for example, to find a, I'll just multiply through everything by s. So that puts an s in the numerator here and cancels out this s. And then we set s equal to 0, which gets rid of this term and just leaves a on the right-hand side. So a, therefore, since s is 0 now, the 4s goes away. We just have minus 0.619, and then that's canceled, and here it goes away, and here it's just a 0.1175. So just doing the arithmetic there, that gives us negative 5.27. And again, looking at the numbers, you see that's about reasonable. That's roughly what you'd expect dividing those two numbers. So again, always check in your head to make sure you didn't make a mistake. That'll avoid a lot of errors. And then to find b, we multiply through by this denominator, the s plus 0.1175, and set s equal to negative 0.1175. That will wipe out this term because it now has 0 in the numerator, and that cancels this, and so we just have 4 times that minus 0.1175. And notice that the 4 multiplies only the s, not the 0.619. Sometimes people like to keep that inside the parentheses, and that, of course, would be totally incorrect. So we have to make sure we get that where it belongs, which is outside the parentheses. And then we have the constant that's still there. And then the denominator, now we just have the s because this is canceled. So that's the minus 0.1175. So now we just put that expression into our calculator, and that works out to 9.27. And again, you can kind of do that a little bit in your head just to make sure that that looks like a reasonable number, but in fact, it's going to be reasonable. It should be about 10, since you got about negative 1 over, negative 0.11, something like that. So it should be about 10, and it is. Okay, so now we'll go ahead and enter those values. And so the a there, I'm going to put a negative 5.27 divided by the s. And remember, we're not entering in the time domain yet. We have to do the partial fraction expansion first before we're allowed to do the inverse transform. So try not to get ahead of yourself because there's no time domain terms that you can put in here. Okay, and then the second would be the 9.27. And then that's divided by the s plus 0.1175. And that should be good now, so we'll check that. And that is correct. So now we've entered the only equation of that type that's needed. So again, we'll click no more equations. And that says we've done it correctly, and we now need to do the inverse Laplace transformation. And for that purpose, if we need it, there is a Laplace transform table that's available there. Now I just select the only option, which is the inverse Laplace transform, and it reminds us that there's an extra set of terms over there which you can use in cases where you need them just by clicking there. Okay, so now I'm not going to need those actually, so I'll just do v naught of t equals. And now we're going to have two terms because this term will give us a unit step function, and this will give us an exponential times a unit step function. So I'm going to need unit step functions next to both, so I'm just going to use brackets to do that. That's the way that it actually wants you to do. So I have a constant term that's going to multiply the u of t outside. So I'll put a closing bracket, and then the u of t function is necessary. And we'll put in the units there are going to be volts again because this is a sought voltage. Okay, so that's the type of terms we need. And then the constant, that's just going to be the value of a here. So we can have the minus 5.27 that we had before in our partial fraction expansion. And then here we're going to have the coefficient, which is the 9.27. And then remember that this is always going to be a decaying exponential unless you had some sort of unstable circuit with dependent sources, which you generally won't have in these problems. So we'll make sure that's always negative. And then the time constant here, since our Laplace transform here normally would be 1 over s plus a, so this would be our rate constant a of 0.1175. So in other words, we need to take its reciprocal to get the time constant that is the form that's used here. So the reciprocal of 0.1175 inverse seconds, is 8.51 seconds. So that's the value we'd enter here. And that should be finished. So now we'll check that equation. That is correct. And now we've entered all the required equations. So I'll click this to complete. And it will always generate the PDF transcript of your work, which you can use later to review or to study. And it'll also show anything you did wrong in red so that you can hopefully learn from that. Okay, so that'll be available on the review work menu. And you do have the option here to see a very detailed explanation here. That's going to be somewhat lengthy in this case, so I'm going to skip it right now. But you do have a chance, if you're unsure about any of the steps that you took, you can certainly view that, which is much like an example. So I'm going to say no for now. And then the review work button would be available here. And that concludes this problem.